In this example, we are going to find the volume of the solid that is formed when we take the region bounded by the graph of the square root of sine x and the x-axis between 0 and pi, and we're going to rotate that region about the x-axis. So here we have a graph of the square root of sine x. We can see that that function has some domain issues. Here's an entire graph of that function. But we're only interested in the region that is between 0 and pi and the x-axis. So this little half egg looking shape right there, that's where we're getting that from. And we are rotating that shape about the x-axis. So as we rotate it, it's going to create kind of an egg shape solid. We're finding the volume of that solid. So I'm going to set up the formula for the volume when we are rotating around a horizontal axis of revolution. So I'm looking at this formula here. That is pi multiplied by the integral from a to b. Our limits of integration are from 0 to pi. We can see that from this inequality here. And then we are integrating r of x squared. Now what r of x is when we draw this rectangle into this region, r of x is the height of that rectangle. Well, how high is that rectangle? It's going as high as the function. So in this case, when we say r of x squared, the r that we are squaring is the function, the square root of sine x. Note that when we square that, we drop the square root and we're just left with the integral from 0 to pi of sine x dx. The integral of sine is negative cosine. So we have pi, I'm going to go to the next line, multiplied by negative cosine x that we need to evaluate from 0 to pi. So we're applying the fundamental theorem of calculus. So here we're going to evaluate this expression. We need to use cosine pi, evaluate cosine at 0, and simplify to give us a final answer of 2 pi. In example 2, we want to find the volume of the solid formed by revolving the region bounded by the graphs of this parabola and this line about the line y is equal to 1. So I'm going to begin by first sketching this region. Sketching these regions is going to be very important for us because depending on what the region looks like will help us determine what the best technique is for finding that volume as we begin to learn more techniques. So I'm going to begin by sketching the parabola 2 minus x squared. It's a parabola that opens downward. It has a vertex at the point 0, 2. And now I'm going to sketch the horizontal line g of x is equal to 1. It's simply a horizontal line that hits the y-axis at 1. So the region that is bounded by those two graphs is this region here that I am shading in gray. Now when I take that region and I rotate it about the line y is equal to 1, here is the line y is equal to 1. It happens to be one of the lines that's bounding our region. We will form kind of a 3D egg shaped, maybe it looks like a football, this shape here. So to find that volume, we need to use the formula pi times the integral from a to b of r of x squared dx, where r of x, I'm thinking about the region that we are rotating. So here is the region that was bounded, right? What I just outlined in black is the region that's being rotated. That region is being rotated along a horizontal axis. We have a horizontal axis of revolution at this horizontal line here, y is equal to 1. When we are rotating around a horizontal axis of revolution, this is the formula that we're looking for here. Let's talk about how we're going to find our r of x. R of x represents the height of a representative rectangle in that region. So I've sketched in this green rectangle. A couple things to observe is that because our axis of revolution is horizontal, because we are rotating about a horizontal line, we need a vertical rectangle. So the rectangle needs to be perpendicular to the axis of revolution. Let's go find what r of x is. How tall is that rectangle? I will find that vertical distance by doing top minus bottom. The top of that rectangle hits the parabola, which is 2 minus x squared. The bottom of that rectangle hits the horizontal line of 1. So I have 2 minus x squared minus 1 to give me 1 minus x squared for my r of x. Another point I will make about r of x is that because our rectangle runs vertically, if we imagine our rectangle hits the x-axis, that means that everything in our integral needs to be written in terms of x. We will see examples where we rotate around a vertical line and everything in our integral needs to be written in terms of y. But let's proceed with this problem. So we have pi times the integral from a to b. To figure out what a and b are, we need to find these x values. What are these x values here that bound that region? To find that, we're going to set these two functions equal to each other. We're interested in when does this parabola touch the line y is equal to 1. So I'm going to solve this equation. I get negative x squared is equal to negative 1, which means x squared is equal to positive 1, which means x is equal to plus or minus 1. So we have a point of intersection when x is negative 1 and another point of intersection when x is positive 1. Those are the limits for our integral. We'll take our r of x, which is the height of that rectangle, 1 minus x squared, and we will square that. And we are integrating with respect to x. I'm first just going to FOIL out what we have on the inside of our integral. And now we will integrate each term individually and apply the fundamental theorem of calculus. So now we have integrated and we're going to evaluate this from negative 1 to 1. And let me not forget that all of this here is multiplied by pi in front. So we have pi. First I'm going to plug in my upper limit of 1. And then I'm going to subtract and plug in my lower limit of negative 1. To give me a final answer, pi multiplied by everything on the inside of the parentheses will come out to be 16 over 15. We should be able to calculate that. So this volume is 16 pi over 15 units cubed. In example 3, we want to set up and evaluate the integral that gives us the volume of the solid when we take the region that is bounded by the line xy is equal to 6. We have another line y is equal to 2, the line x is equal to 6, and we're revolving around x is equal to 6. So first, let us just set up this region. I begin by sketching my x and y axes. Do make sure that you label your axes. That first equation, xy equals 6, we don't typically see equations given to us like xy is equal to 6. It may look more familiar if we solve it for y to see that y is equal to 6 over x. And then we can say, oh, that's just the reciprocal function stretched vertically by a factor of 6. You think back to pre-calculus, the reciprocal function was one of our parent functions. That graph looks like that. So there in red is the equation xy equals 6. Then I have a horizontal line of y is equal to 2. Here is that horizontal line of y equal 2. I have a vertical line of x is equal to 6. Here is the vertical line of x is equal to 6. So the region that we are working with is this region right here. And we're going to take that region and revolve it around the line x is equal to 6. So I'm taking this region. I'm going to just outline the region that we're working with. And we're spinning this region around that green line. So we'll end up with another piece that looks something like this. So kind of give us a 3D shape of a bowl. Okay. So to find volume, we're using the disk method. Volume is pi, the integral from a to b. This time we're rotating around a vertical axis of revolution. We're rotating about x equal to 6. That's vertical. So on the inside of our integral, I don't have r of x squared, but I have r of y squared dy. And I know that everything in this integral needs to be in terms of y, because when I come in to draw my representative rectangle, that rectangle needs to be perpendicular to the axis of revolution and extend all the way out to covering the region that we are rotating. So that horizontal distance right there is going to be our r of y. And to figure out what that expression is, I erased my axis of revolution, x is equal to 6. But to figure out what that is, instead of doing top minus bottom, if you think back to example 2, our representative rectangle was vertical here in green, and we did top minus bottom. Down here, our representative rectangle is horizontal, so we're going to do right minus left. The right end of that rectangle is on the vertical line of x is equal to 6. The left end of that rectangle is hitting the red graph right here. Remember that that red graph is the equation xy is equal to 6. But I want to be able to write that equation in terms of y. So I'm going to solve for x. Solving for x gives me x is equal to 6 over y. So for the left side of that, we are subtracting 6 over y. So now that we have r of y, let's make sure that we find our limits of integration, our a and b. Remember, we're integrating in terms of y. So to find our limits of integration, we need to know what is this y value down here and what is this y value up here. We're interested in what these y values are. The y value at the bottom, this y value down here, happens when the vertical line of x is equal to 6 touches the red graph. So this point down here happens when 6 is equal to 6 over y. So I took the x value of 6 from the green equation and set it equal to the expression for x for the red graph. Solving that tells me that y is equal to 1. So this is not drawn to scale, but our lower limit here is 1. Let's find the upper limit of our integration. To find the upper limit of this integration, it happens simply at 2, right? That's at the horizontal line of y is equal to 2, so we don't really have to do any work for that. So now we can proceed with evaluating our integral. We have pi multiplied by the integral from 1 to 2 of r of y, which is 6 minus 6 over y, and we're going to square that, and we're integrating with respect to y. Let's go ahead and do some algebra on the inside of the integral to FOIL that expression out, expand that out using the distributive property. Here's what we get when we multiply that out. Because we're going to be integrating, I'm going to take some time to rewrite what's on the inside of the integral, at least some of these terms. The 72 over y term will probably be best integrated written as it is, because that's a natural log rule, but the last term I will rewrite as 36y to the negative 2. Now I'm ready to start integrating. The integral of 36 is 36y. The integral of negative 72 over y is minus 72 natural log absolute value of y. And the integral of 36y to the negative 2 is 36y to the negative 1 divided by negative 1. And all of this needs to be evaluated from 1 to 2. So first, applying fundamental theorem of calculus, we'll plug in our upper limit of 2. So we have 36 times 2 minus 72 multiplied by natural log of 2 minus 36 divided by 2. If it's helpful for you, this term here is just a negative 36 divided by y when I rewrite that term. So I plugged in my upper limit. Now I'm going to subtract and plug in my lower limit. So I have 36 multiplied by 1 minus 72 natural log of 1 minus 36 divided by 1. We still have the pi on the outside, and let's work on simplifying this expression on the inside. 36 times 2 is 72. We're subtracting 72 natural log of 2. 36 divided by 2 is 18. Let's distribute this negative. Minus 36. Natural log of 1 is 0. This last 36 here is negative, and we're distributing this minus sign to it, so we're going to end up with a plus 36 in there. Our 36's will cancel. Inside of the parentheses, we'll combine like terms. 72 minus 18 gives us 54, and we will subtract 72 natural log of 2. And this gives us our final answer for the volume of that region.